Welcome to This Explainer. Today, we're popping the hood on AI and chatbots to see how computers actually process human language. I mean, we interact with these machines every single day, right? We're constantly typing quick questions into our phones, relying on autocomplete, and getting surprisingly human-like answers back in an absolute instant. But what's actually happening behind the screen? How does a machine, a system that fundamentally only understands ones and zeros, read and comprehend the nuanced, chaotic text that we type? Let's find out together.
Okay, let's kick things off with a real blast from the past. We're going back to 1966 to look at an early natural language processing system named ELIZA. Picture a user sitting down at one of those massive, clunky computer terminals. They type out this incredibly vulnerable statement, "I need some help. That much seems certain."
And ELIZA fires back with, "What would it mean to you if you got some help?" It's pretty wild to think about now, but ELIZA made users feel deeply understood. People would literally sit at these terminals for hours, pouring their hearts out, truly believing the machine empathized with them. But the truth? It was just a crude mechanical mirroring trick. ELIZA was programmed to act like a Rogerian psychotherapist. It basically used simple pattern matching to find a phrase like, "I need X," and just mathematically flipped it into, "What would it mean to you if you got X?" It was a brilliant but incredibly fragile illusion. So that brings us to a fascinating question, and it's really the one that drives the rest of our explainer. If modern machines aren't using those simple parlor tricks anymore, how do they actually pull this off? How do modern microchips process the poetry of Shakespeare, the brevity of social media hashtags, and literally everything in between? Section 1. The illusion of understanding. We're going to break this chatbot illusion and zoom all the way down into the true anatomy of machine reading, starting with the very foundation. To teach a machine to read, we first have to translate the absolute chaos of human language into strict structural order. Think about how messy we are when we communicate. When we speak or text, we use slang, we make typos all the time. We say and or we just trail off and cut our words in half. It's totally organic and completely unpredictable. Computers, on the other hand, they require rigid mathematical rules. They're processing logic gates and binary states. So, to get a machine to read, we have to somehow engineer a bridge across that massive gap between human chaos and digital order. Section 2. What exactly is a word? It sounds like a simple question, right? But for a computer trying to process global languages, it's an absolute nightmare. This perfectly illustrates the cross-cultural problem we're dealing with. When we look at how languages build meaning using smaller units called morphemes, we see some incredible extremes. Take an isolating language like Vietnamese, which uses tiny, single-unit words, super clean. But then go to the exact opposite end of the spectrum with a polysynthetic language like Koryak, spoken in Russia. It can fuse an entire sentence, something like, "I sewed a lot of yurt covers in the middle of a night," into one single massive word. How is a computer supposed to build a standardized dictionary with that much structural variation? Now, to really grasp the scale here, we got to look at Hürden's law, also known as Heap's law. This is a mathematical law that basically proves the number of new words in any language literally never stops growing. Just think about the massive jump in data between eras. Shakespeare used about 31,000 unique word types, but flash forward to the Google Ngrams corpus, and there are over 13 million unique word types. Because we are constantly inventing new slang, mashing up acronyms, and dropping new brand names, a machine will inevitably encounter words it has never seen before. It's a massive unknown word problem. Section 3. Representing text with Unicode. Because words are way too unpredictable and theoretically infinite, machines have to zoom all the way into the character level to standardize the mess. They need a universal alphabet. Consider this massive number for a second. 1,114,111. That's the total number of unique abstract code points available in the Unicode standard. Unicode is this modern system that assigns a unique mathematical ID to every single character in existence. We're talking about everything from the English alphabet to Chinese characters to ancient Sumerian cuneiform, right down to the exact graphical emojis you're sending on your phone. Every single symbol gets a permanent, standardized ID card. But we can't just store millions of huge numbers inefficiently, or every simple text file would be gigabytes in size. To save digital space, the world relies on the UTF-8 encoding system. It is a brilliant variable length system that acts like a sliding scale of memory. It efficiently uses just one single byte of data for common characters, like basic English letters, keeping things light and incredibly fast. But it dynamically expands to use up to 4 bytes when you need to type complex scripts or drop in your favorite emojis. Section 4. slicing language with tokenization. So the crucial point here is that since full words are too big and infinite, and individual characters are too small to carry real meaning, computers find a middle ground. They slice language into manageable chunks called tokens.
To figure out the perfect token sizes, modern AI uses a data-driven algorithm called byte-pair encoding, or BPE. It's literally like snapping Lego blocks together. First, the algorithm starts by looking at individual characters in a massive training text. Next, it iteratively merges the most frequent neighboring characters. If it sees an N and an E sitting next to each other all the time, it merges them into a brand new token, NE. If NE sits next to W a lot, it merges them into new. Step by step, it builds a custom vocabulary of subwords based entirely on pure mathematical frequency.
It's highly effective, but here's the catch. There's a stark mechanical difference in how it handles different languages. Because modern AI training data is heavily dominated by English text, an English sentence like, "in a deep bowl," is perfectly sliced word by word. But consider the Spanish translation. The word for deep, hondo, gets chopped into H and ondo. This oversegmentation literally fractures the language. It forces the machine to process far more individual tokens just to represent the exact same meaning in Spanish, which actually costs more time and computing power to run. Section 5. Finding patterns with regex. Before slicing those tokens up, the computer needs strict rules to hunt down spaces, punctuation, and boundaries in a sea of text. This is where regular expressions come in. Regular expressions, or regex, are totally the unsung heroes of software engineering. Think of them as algebraic wildcards for text. They allow machines to search massive documents for incredibly complex patterns using just a few specific symbols. The clean star lets a machine find 0 or more occurrences of a character. The question mark looks for an optional character, like the U in the British spelling of the word color, and the plus sign strictly looks for 1 or more occurrences. For example, imagine trying to program a computer to read sheep language. A sheep might say a short ba or a really long ba. We can use the clean plus to write a tiny regular expression. The letter B followed by A with a plus sign and an exclamation mark. That simple little line of code perfectly captures the infinite variations of a sheep's bleat. It is an incredibly elegant tool for standardizing messy, repetitive inputs. Section 6. Measuring distance between strings. Finally, once a computer has sliced up text into tokens and found its patterns, how does it mathematically know if you made a spelling mistake or if a speech-to-text program heard you correctly? It needs a way to measure the distance between words. It uses an algorithm called minimum edit distance. This is a dynamic programming alignment that measures exactly how many mechanical operations it takes to transform one string of text into another. Imagine transforming the word intention into execution. The computer calculates the cheapest path. It deletes the I, substitutes the N for an E, substitutes the T for an X, inserts a U, and substitutes an N for a C. It mathematically calculates that the specific distance between these two words is exactly 5 edits. This hidden math is exactly how your phone's autocorrect knows what you actually meant to type. So, we've seen how machines turn our chaotic language into Unicode, how they slice it into subword tokens using algorithms like BPE, and how they mathematically map our spelling using edit distances. As we wrap up this explainer, I'm going to leave you with this provocative thought to chew on the next time you chat with an AI. If we teach computers to perfectly slice, encode, search, and measure our words with all this brilliant math, do they finally understand us? Or are they just imitating us better than Eliza did back in 1966? Thanks for exploring this with me, and keep questioning the incredible technology working silently behind the screen.